is just about generalities about character theory, so just the basics of characters of representations of SL2R. So we'll start by recalling what characters of finite groups are and try to imitate that situation. So the warm-up is G finite. So this was, I'll just recall what I did at the end of my second lecture on finite groups all the way back last Monday. And so we had that the group algebra, which remember we viewed as functions on G with the convolution operation. This was a left and right representation of G. You could translate on the left, translate on the right. So it's a G cross G representation. And it's a G cross G representation. It was isomorphic. Well, the sum was over every irreducible representation of G. And we could write it like that. Maybe I wrote it the other way. So before I used the tilde notation for the linear dual. Maybe now I'll go back to using the star notation for linear dual. Because tilde means k finite dual, which in this case doesn't have any import, but later it will. Okay, so this was as a G cross G representation. Remember, that's what the box tensor product meant. That this was the external tensor product. The left copy of G acted here, the right copy acted here. And as a diagonal G representation, it was the same thing as, well, that was just a notational issue where you change the external tensor product to the internal one. And let's see, so then we had a little, so we're interested in class functions. Class functions on G, which were by definition functions that were invariant under conjugation. Okay. And according to this decomposition, a class function is just a function on G that's invariant for the diagonal action, right? The conjugation action was exactly the conjugation action was the diagonal of the left action. Maybe it's a little bit more transparent if I put the inverse here, because that's usually where we've been writing the inverse. So if I have something that's invariant under the diagonal left and right action, that means it's conjugation invariant. So we just deduce that this is isomorphic as a direct sum of the G invariance, the diagonal G invariance in the external tensor product, or the G invariance in the internal tensor product. Okay. So then we have a little basic linear algebra. And this is the part that I think, this is the part that I kind of made a little bit of a mess of at the end of that second talk last Monday. And the basic linear algebra, as Dragan pointed out to me, is just this. So let me do something slightly obtuse here. So I'll write this before I get to that basic linear algebra, I'll do a dirty trick. So you'll see why I want to view, why I want to add an extra star here. So if I star, I can bring the star, and then the double star is canonically isomorphic to no star. So this is certainly true.
What is the difference between G tilde and G hat?
No difference. There's everything down here is G hat. Equivalence classes of irreducible representation. So the basic linear algebra fact was that we have this following diagram. We have this. Oh, maybe I should leave a little space at the top to draw them out. Just going to NV. So there's the isomorphism that takes V star tensor V to the endomorphism that eats W and spits out V star of W V. So it's this canonical isomorphism. Then there's the evaluation map down to C, which takes V star, V star tensor V to just the evaluation there. And this is an isomorphism, so there's a unique map which makes this diagram commute. Okay? And what's the map that makes this diagram commute? The trace, the trace. Okay. So in fact, in fact, this diagram, so this is the basic linear algebra part. The slightly less basic linear algebra part is that this is, all these maps are G-invariant maps, or it's a G cross G map to here. You can think of this as the trivial representation. So is G equivariant. So what that, and so if we took G invariants everywhere, so we have we still have the trace evaluation homomorphism. But we know that the G invariants in endomorphisms from V to V by Schur's lemma, that's just C. So at the end of the day, we can go back and apply that situation to this chain of isomorphisms. We're interested in decomposing class functions. Well, there's a unique G invariant map from V star, a V pi star tensor V pi dual, V star tensor V pi to C. That G invariant map corresponds to the trace. And so that this is just the sum over C of chi pi, pi and G hat. Where if you unwind everything, chi pi of G is just the character, the trace of pi of G. Character of pi. So let me just isolate. So, okay, so that gives a treatment that we're going to try to imitate of decomposing class functions on G. So let me just state the main properties of characters that follow from this. So, all right. So the first is that chi pi is conjugation invariant. Maybe that should be the zeroth property, but we're going to want to imitate that. Of course, it's conjugation invariant. We're interested in decomposing class functions, so that was built into all of this. If you want, it's built into properties of the trace. The other thing is that the characters of irreducibles well, they're linearly independent. That's the part that we're most interested in generalizing. But in fact, they form a basis of class functions, or a basis of class functions. That's just what this isomorphism says. And another property of the trace, which is important, is that it's additive on short exact sequences. So if this is a sequence of representations, the character of V is just the character of U plus the character of W. If I take the trace of a block diagonal of a matrix which is in block diagonal form, that's just the sum of the traces of each of the block diagonals. So those are the key properties of the trace. They form a basis of conjugation invariant functions on G. They're additive on short exact sequences. So that's what we want to imitate for infinite dimensional representations of G. So we just follow our noses and see what happens. So we're just going to follow our noses for a few minutes.
Could you remind me about the class functions along the
What about class functions?
could you remind me about the
Okay,
class
so the definition was written down. I just erased it, unfortunately. So a class function, f from G to C, is one that's constant on conjugacy classes. So there's one such that f of G x G inverse equals f of x for all x and G. So you're a methodical note taker. That was one of the first things that's already in your notes, I guarantee it. Okay, so, but it's hard to write and think at the same time. I know, so. Okay, so imitate for SL2R. So we just want to we want to define the character of a representation and hope it has a nice property. So we fix, say, a continuous admissible, and we'll see that this is really a crucial property, admissible representation. Pi G, to say bounded linear invertible operators. Why don't we fix a Hilbert space H, say, Hilbert space. And so we just define the character of pi to be the trace of this bounded linear invertible operator on H. So is there any problem with that definition? Well, there's a couple problems. The main problem is that, of course, H is infinite dimensional. What does it mean for an operator to have a trace? Does it have a trace? Does the identity operator from H to H have a trace? That would be like adding ones up infinitely many times. That doesn't look like if H is infinite dimensional, well, you've got two problems. The main problem is what does trace mean? And does trace of pi of g exist? Well, you could imagine definitions of traces in Hilbert spaces. You take an orthonormal basis and sum the diagonals, say, and that.
Just before you erase this.
Okay.
I can see how it is a direct sum of c's for each pi in g hat.
Yeah.
But where did you get that chi pi from? I mean, you've suddenly gone inside CG from.
Yeah. So I.
Left-hand side is just a representational space.
Yeah. So you understand that this is
Yes.
that there's a unique.
It is a c.
This is a copy of C,
Right.
and there's some function in here, and that function.
Function on g.
Well, there's some functional from V star tensor V to C,
Right.
which spans that, and that's the evaluation map.
Exactly.
Okay. The evaluation map corresponds to the trace.
Okay.
Okay. Now there's one other thing that we have that I didn't say is that we viewed this space as the space of matrix coefficients of pi.
Okay.
So then the trace corresponds to adding up the diagonal matrix coefficients, which is this. So yes, I did skip a step in. So there's some. It's not even a dangerous bend. There's just some skipped one step. So it's clear that it's a multiple of some chi pi, and then you can take chi pi to be this. Okay. Okay. So I was back. We were talking about traces of operators on Hilbert space. You could imagine a good definition of trace would be that take an orthonormal basis, write down this infinite dimensional matrix, sum up the diagonal. If that sum is finite and doesn't depend on the choice of basis, that might be the trace of an operator on Hilbert space. But of course, that seems like a good definition. I think it is a good definition, perhaps. But even with that definition, the trace of the identity map doesn't exist. So we're a little bit stuck. So what do we do? So, well, we'll go back to finite groups a little bit and do something slightly obtuse. So let's think about so we know we have this equivalence, which is sometimes conceptually helpful. We have representations of G, and sometimes it's better to think of that category as the category of C of G modules. And for instance, if we have a representation pi on vector space V, that corresponds to the module where the function f in C of G acts on V by just averaging over the group. That's the correspondence on objects in these categories. So the character chi pi, well, that corresponds to the trace of this operator pi of f. the character was the trace of pi of g, under this equivalence, the corresponding idea would be looking at the trace of the action of an element f in the group algebra. Well, here's a formula for it. It's just f of g, well, I'll write it like this, the trace of f of g, pi of g, v. And this is stupid. This is an obtuse thing to do, as I said, because, of course, in this case, trace commutes with finite sum. And we just have the sum of f of g, the trace of this. So it's just the average, i.e., the average of chi pi of g over g weighted by this function f in the group algebra, function on g. As I said, it's a stupid thing to do because if we have this average character, we can, of course, recover the original character just by putting in the function that's 1 on the group element g and 0 everywhere else, and then the trace of the operator pi of that indicator function of an element is just the character evaluated at g. But there's a seed of an idea in here that is going to work in the infinite dimensional case. And the idea is that we may not be able to evaluate, say, the trace of, in any sensible definition of the trace, we may not be able to evaluate the trace of pi of g in this infinite dimensional setting. But in an average where a point has measure 0, contributes nothing, we may be able to get something finite in the end in this averaging procedure. Because unlike the finite group case, a point has no mass with respect to hard measure. So in an average, even if the trace is undefined at a point, that doesn't mean the average blows up because the point has no mass. So the idea is take f, a function, so idea, and so we're back to SL2 now, or not even SL2R, any, say, semi-simple Lie group, real semi-simple Lie group, back to SL2, but let's continue with SL2R. The idea is take a function from SL2R to C and consider, well, consider pi of f, this operator, which is by definition, we've seen it many times before, the average of pi of g over the group weighted by the coefficients of f. And this is a map from V to V. Well, H to H. I guess I'm using H for my representation. That was probably a stupid thing to do because I'll keep making that mistake. And then
why is this necessarily an operator since we're not integrating over a compact group?
right, so I'm being vague here. So you're right, there's all kinds of problems of convergence in general, say, if I take some nasty function on SL2R, but I'm just writing down an idea that we're going to make more precise. Okay, and then define this map, theta, which takes f to the trace of this operator pi of f. So again, this is an operator in infinite dimensional space. We haven't made sense of even what a trace means. We're going to have to do that. But this looks like a good idea, and this is related to Jonathan's point. Well, let's say f is a nice function, smooth and compactly supported on G. Because then you can imagine that this is going to be no problem, or there'll be, you would imagine not encountering as many potential convergence problems if f is a nice compactly supported function on G. Okay? So G is SL2. Okay, but we still have to make sense of what we mean. So even if f is nice, compactly supported, so we're integrating, this integral makes sense as an operator from H to H, we still have to make sense of what the trace of an operator in infinite dimensional space means. And the only intuition that you have is that, well, your trace is on finite dimensional spaces. So we'll try to reduce to that case. And so we. And so, and the idea is use admissibility, use the finiteness of admissibility, the finiteness in the K-type decomposition to reduce to the finite dimensional case, which we do understand. Okay. So that's what we're going to do. We're going to try to use the fact that we're not talking about an arbitrary representation, but when we restrict it to K, each K-type occurs with finite multiplicity. We know how to define traces on finite dimensional vector spaces. So if we're going to try to pursue that idea, then it's not good. We want to take an F that's somehow adapted to the K structure. We want to take advantage of the restriction of H to K. If F has no good properties under transformation by K, then we can't hope that this operator will preserve that nice admissible K decomposition in any way. So, so instead of considering F in C infinity, so an arbitrary function at compact support, instead consider, motivated by these ideas of admissibility, instead consider these K-finite functions, which are smooth of compact support. So we should take F compactly supported on G, such that the dimension of the span of the functions that I get by transforming under the left and right action, these functions that I get by transforming F by the left and right action of K, that's a finite dimensional space. So this new set of functions that we're considering are smooth of compact support, but when we smear them out by the left or the right action of K, all those functions, after being smeared out, live in some finite dimensional space of functions. Okay. Now, this is potentially useful if and only if, well, you would imagine that this is potentially useful in defining a trace for a function of an arbitrary function of compact support, if and only if this is dense in here. Okay? And that's true. So let me just say some facts about. This is a useful idea. Well, kind of a zeroth fact is that this is actually an algebra, is closed under convolution. That's an easy check. It's easy. You can just write it down. Write down the definition of convolution. So closed under star, which is equals convolution. So it's an algebra unto itself. And the other fact is that it's dense in the space of all compactly supported functions on G. Okay, so now we're getting to, I have to mention some words about what this means. I mean, to say that a space is dense in another space means there's a topology floating around, right? So this came up when Bill was talking about distributions. Distribution is a linear functional on a space of functions that's continuous. So there are all these, you have to consider topologies on spaces of functions. So the topology on this space of functions is the so-called Schwartz topology. So convergence here means, so I'll put it in quotes and I'll explain why the quotes means convergence, uniform convergence of all derivatives of all derivatives. So a sequence of functions converges to another function if, well, I'll say in quotations, if that sequence of functions converges uniformly to the limit function, and not only not only the functions converge, but all derivatives converge. Okay? Now, that in fact is only precise if all the functions in your sequence are supported in a fixed compact set. So you can remove the quotes. If you have a sequence of functions, all of whose supports are in a fixed compact set, they converge to a limit if and only if they converge uniformly on that compact set, and so do all their derivatives. There's something about, well, what happens, how you put different compact sets together. You have to take some sort of limit of these quotations. But I'm not going to emphasize that. But that's the natural topology. It rises all the time. Those of you who've seen it, you've seen it a million times before, and you know why it works. If you haven't seen it, then giving a dissertation on the definition, why it's a good definition, isn't going to sink in. So I'll just give you some sort of heuristic. Okay, so yeah. Okay, so what I've written down, I want my function to be compactly supported on G, and I want to look at all other functions that I get by taking an element on G and evaluating it on and I get a new function by translating on the left by K1 and translating on the right by K2. So this is a new function that eats x and spits out the original function at this point, translated on the left by K1 and translated on the right by K2. So I'm just looking at the span of f under the left and right regular actions of K. So I get a whole family of functions by acting on the left by K, acting on the right by K, and I'm demanding that what I get from f by left and right translation by K, they all live in a finite dimensional space. Yeah, exactly. So by K finite invariant functions. So yeah. So for instance, if K1 equals K2, if they're constant on K conjugacy classes, they live in here automatically.
And spherical functions always span one-dimensional subspace.
Yeah. Yeah. So I mean, we were talking.
Even for arbitrary data.
So let me just say, so these are by K invariant, by K finite functions on G. Right, so we had examples, all kinds of examples. We're looking at tau spherical matrix coefficients, NM spherical matrix coefficients. They translated on the left by the character N. They translated on the right by the character M. These were Mn spherical functions, and the dimension of this span then is one-dimensional, so they definitely live in here. Okay. And you could, so this is the place that matrix coefficients of Harishandra modules naturally live, right?
Shouldn't the spherical functions themselves are dense in CCFW?
Yes.
So that would automatically.
I mean, you have to take on the spherical functions the eigenfunction on the left and right. So you have to take their linear combinations. And of course, here he's assuming compact support, and no spherical function which is eigenvalue of Casimir will have a compact support because such functions are analytic. So
this is precisely the point of introducing those other growth conditions.
Yeah.
I mean,
Okay.
here the good thing to think about is think about the proof of 2. What 2 says, you take arbitrary smooth compactly supported function, act by K. This is action of a circle, so you get a function of K, write it down as Fourier series for left and right, and then you will have this Fourier series where the coefficients will be K finite on left and right. So this is basically approximating arbitrary smooth function by a finite Fourier series for left with Fourier sums on left and right.
I thought that's what the spherical functions meant for you.
Yes, but there you are fixing just one frequency. Here you have linear combinations.
Depends what you mean by spherical function. You may think a spherical function is just something that's left and right.
I was thinking of S and N.
No, he's thinking what I used the last week.
Dimensional matrix coefficients.
Yes.
Yeah, so if you think of spherical functions, they transform by the character on the left by n and the character on the right by m, and not necessarily coming from any Harshchandra module or anything like that, then Dragon's argument is an argument for the density of this space in this. You take such a function, you write down it's by S1 cross S1 Fourier series. That's a sum of spherical functions whose, when you spread them out, the span is just one-dimensional. So.
So in this case, this is just linear combinations of all compactly supported smooth spherical functions.
Yes.
Can
Okay.
I differentiate K defining function by action of element of any object of G?
Yes. Yeah.
Do I get again a function?
Yes. Yes. So this space will be invariant. Is G finite as well? Is finite for? Well, let's see. Yeah. I mean, this space is. You can differentiate the actions, the left and right actions of all of G. Preserve that. Okay. Okay. So.
There is a question.
Oh, sorry.
Could you explain explain again the uniform convergence of all derivatives?
Okay, so this is precisely the thing that I'm not going to explain well. Okay, but I'll explain it in the case where, I'll explain it in the easy case. So what does it mean for a sequence of functions in this space to converge? Okay, that's what I'm supposed to tell you. And I'm not going to tell you the general answer. I'm going to tell you the answer when all of those functions have support in a fixed compact set. Question?
So, but they converge if and only if there is such a compact set.
Right, but that's okay.
So you can answer
Okay.
the question very easily.
Oh, okay.
Yeah,
So,
I mean,
oh,
it's-
well, why am I getting? Yeah. Okay.
Because he asked you,
Yeah. Okay. Sorry. Okay. All right. I'm being stupid. So yeah. Okay. So a sequence of functions converges in this space if and only if there exists a fixed compact set where they're all supported. In that fixed compact set, you require uniform convergence of the sequence and all the derivatives of the sequence. Yes. Yes, uniformly. Why you look perplexed?
Is it a function uniform converge implies that all the derivatives converge uniformly?
No,
No, not at all.
no. This is much stronger than just saying the functions converge uniformly.
You can have lots of wiggles in the function as it converges. The Stanley example is a Newton's conversion.
Yeah. So this is something stronger. Question?
Is the reason that you can't just always consider K that it may not be differentiable at the boundary of the compact sets?
If I can't always.
Just, they're all defined in K, right? Because it has
Ah.
the differentiation of the.
Well, wait. There's K sometimes means a compact set, but here it means this compact subgroup.
The maximal compact, right? So
Right.
No,
No, but these aren't.
Set, not subgroups.
Yeah. So yeah.
They are very large compact sets, much bigger than K.
Yeah.
Yeah. So there are too many Ks. in the thing.
But there's not too many Ks on the board. There's too many Ks in my mouth, I think. So, okay.
So
so,
you can always deny.
so yeah. So there are larger compact subsets than the group K. So,
This is K for compact.
yeah, K for compact in German. So, okay.
Why did you say this was a natural space for matrix coefficients of Harshchandra modules?
Because okay. So no. Then I misspoke because they're not compactly supported. So no. That was a thing that I'm glad I didn't write down.
All
Cause,
of
so,
the C and the shorts, all those things. Matrix coefficients look at those things.
yeah, So yeah. You have to abandon compact support to look at matrix coefficients, of course. So I mean, we've seen expansions of matrix coefficients in this variable a, this a variable, and they don't have compact support. They live everywhere. So that was just some garbage that flowed forth.
No, I don't think I think what you said was correct. You said that this is a natural space when you look at our Chandra modules, but you didn't say that you will integrate this with matrix coefficients.
Okay. So someone says that garbage didn't flow from my mouth. Okay.
So K doesn't have to be that specific thing.
So let me write down what uniform convergence means. So because that's where the other K was arising. So F1, F2, and so forth converges in C infinity C G if and only if there exists a compact set. Well, I won't call it C, I won't call it K, I'll call it SC. Or U. U is better. U. No, U is a V. No, V is a S. S and G. Omega. That looks better. Yeah. Okay. S, 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 no, K2. No. Compact subset F such that the support of Fi is all contained in S, and well, I'll write it somewhat imprecisely.
Now I'm in trouble.
Yeah.
I just put a bunch of differential operators.
Yeah, D. So this converges to F in here, converges to DF uniformly on K, on S, for all differential operators. D.
But I mean, it's important to stress here that you fix D and then you have uniform convergence, then it's
And
no
yeah.
uniformity over D's.
Yeah, so for each differential operator D, maybe it's better to put that up there. So for each, so fixed differential operator, look at the sequence, demand uniform convergence of that sequence. Of course, you can't demand.
Why don't we start the Schwarz space in the beginning? I mean,
What?
in the Schwarz space of G.
Why not use that?
Yeah.
Well, look, we're trying to reduce the trace to finite, to some finite dimensional spaces.
But I mean, we don't know yet what this Schwarz space is.
No, but you can't because a priori matrix coefficients of representations can grow very fast. So the only thing you know that they're bounded on compact sets. And
I mean, if we have a
no, they're polynomially growing in A. I mean, they definitely don't extend to Alexander-Schwarz space.
Yeah, oh,
No.
yeah, no, they don't. They extend to my other Schwarzes.
Yes, but
So the point is, let me say the following. You start with CC infinity because you know that everything's there, and then eventually you extend to various spaces depending on various things. It's a place, the CC infinity is a place to start. Because everything works out, for sure.
Yeah, I mean, it seems. I don't. It doesn't. I mean, it seems like the most reasonable place to start. I mean, why would you want to start with something more complicated where you impose growth conditions at infinity rather than just zero condition at infinity? I can't see a more natural.
previous talk that we said we can integrate against. I mean, if
I-
phi of G
I-
satisfies some
I-
conditions, then we can integrate.
I agree. It may be interesting to look at these questions for different spaces of functions. But if we're just getting started, we should look at the simplest space of functions, where we don't have any condition. There's nothing at infinity. This is the way it is. Listen to Professor Hecht. He'll. He knows this is the way it is. Yeah.
I mean, if you look at some space of functions with growth, then you get in trouble with differential operators because you have to control growth of differential operators. So this is the simplest object you can have because here basically you want that in any chart you have convergence all derivatives of functions, and you can do this so easily only on compact sets. And you can just bound everything when you change coordinates and things.
Okay.
You will see in the afternoon when I discuss Harshchandra-Schwartz space, then you have to use left and right invariant differential operators and do a bunch of messy technical assumptions to make sense of this.
Okay. So let's see how this algebra is going to help us reduce the infinite trace to finite trace. So let me just make a definition. So finite rank endomorphisms of a vector space V are just defined to be maps from V to V, endomorphisms of V, such that the dimension of their image is finite. Okay? And the lemma is that if F is in this space, and this is the whole point, and V in let's see, how do I want to say this? Yeah, so then on K finite vectors, then this pi of F is a finite rank endomorphism of the K finite vectors in this representation that we started with. So if we start, we're starting with the representation we wanted to find the trace. Well, we're going to use the admissibility on of the K, well, the admissibility, so that leads to the K finite vectors, and these functions will be finite rank endomorphisms of the K finite vectors in H. Okay? So how would you prove something like this? Is this a horrible? Is this hard or is this easy? Well, you just write everything down, and it's not. It's very easy. It's just so you fix a K finite vector. Okay, and then you just compute. Well, maybe I'll just even isolate the statement. Let me isolate the first statement. So you first check. That pi of k, pi of f, is simply pi of, well, what I get by left translation by k applied to f. So this is just well, let's write it down. So y, just to illustrate how simple this is. So pi of k, pi of f, we simply write down what f is. So this is pi of k applied to f of g, pi of g dg. Okay, so now I bring my pi of k in, use that pi as a homomorphism, and then change coordinates. So maybe I'll write an extra step. So this is pi of kg dg. And finally, do up here. So this is the integral of f of k inverse of g over pi of g dg, which is pi of lk of f. But that's the only thing you have to check, because if I apply this operator pi of f to a k finite vector, and I see what I get when I smear things out, well, f transforms in a finite space. The space is finite dimensional, and the space that I get by smearing things out, and so I'm going to end up the image of this will have finite dimension.
Where do you use the right finiteness to show that it shows in the resolution?
Let's see. So
You don't need it there.
no, I guess to make it. Let's see. So in algebra. No. So are the left. Let's see. So maybe you need it there. Do you need it there to make? Are the left k finite ones in algebra as well? So you just have to write down the convolution. Maybe you need it there. For you definitely need. I guess for the. I don't know. What do you? I mean, in these Fourier series, it's natural to take it because in this density argument, what's appearing, the Fourier terms, are left and right. Okay, fine. I mean, this is so.
I mean, you still didn't do the last step when you will claim that the character is basically a sum of k finite matrix coefficients, and there you this is some symmetry thing which will become apparent at the end, but
So far, we haven't used it.
I mean, the point, I mean, whatever it's used, I'm not sure that it was not used, but let's assume that it was not used. But the reason why all of this makes sense, because Peter is assuming that you have a representation of the group, and this is a space of k-finite vectors. If you do not assume this, then you are in trouble, because this phi of f won't make sense if you just have k-finiteness on one side.
So let's go back to our basic linear algebra statement that appeared for finite groups. Well, we were looking at the linear dual V tensor V, and we mapped it to end C of V. And the map, remember, was just a dual vector and a normal vector got sent to the function which takes W to the dual vector applied to W on V. Okay, the usual map. But it's obvious that the image of this, well, what's the image of the corresponding transformation? It's finite rank. I mean, the image is just spanned by V. So we're actually landing in finite rank, finite endomorphisms. What did I call them? Finite rank endomorphisms? Whatever, Fn. We still have evaluation down to C. We'd like to complete this to define our trace. And the only thing you have to know is that this is an isomorphism. So maybe this is not, there's a little more to check in this case. So this map is an isomorphism. So then I can define the composite of going back and then evaluating to be trace. This defines the trace. Yeah.
Over here, you started to write fix V and HK
Yeah.
to show that pi of actually landed in there. And I must have missed your argument after you said that pi k pi f equals pi of LKF. What was the argument?
Okay. So what I checked is that when I translate by k on, so if I follow pi of f by pi of k, I get something living. I get pi of something in a finite dimensional space. Okay. Then, but what is the definition? So now this is terrible board technique. But pi of f applied to a k finite vector is the integral of f of g pi of g v dg. Okay. So this is k finite. Let's see. So wait, now this is confusing me. Wait, what's going on here? Hang on a second. No, I guess, did I use the fact that V was k finite? I have to use it, yes, but why? So I want to see that
No, you apply pi k
to this.
and then you use invariance of the measure,
Oh.
and you get a formula which connects with this formula
Yeah.
in the top
Okay.
right corner.
Yeah, let me just do it slowly, so because I even managed to confuse myself. So okay, there's. So we're finishing this lemma. So now look at pi of f applied to a k finite vector. Okay. So that equals the integral over g of f of g pi of g v dg. And I want to see that this remains k finite. So let's see. So I apply pi of k to pi of f of v, and I get pi of LK f of V. So what I get after applying f to V and translating by K is all living in this finite dimensional space spanned by, I mean, the span of the LK of f's is finite dimensional. And so this is going to be live in a finite dimensional space. Right?
So you don't use the fact that V is k-finite.
So where are we using that as k-finite?
Use it F is k-finite.
We're using f as k-finite. Definitely using f as k-finite, but V being k-finite.
Yeah, but I mean, it sounds like what you're saying is that HK is finite dimensional, so that the morphisms would automatically be finite dimensional. I'm confused on something you're saying.
No, HK is infinite dimensional.
So what do you mean by this?
The
V
image
is
does not have to be finite dimensional if V is not k-finite for all of the vectors, right? I mean, because that's for each V we know that's finite dimensional, but there's a lot of V's.
Yeah.
If they're not k-finite, then you won't necessarily have that the image is finite dimensional.
Oh, no, but Peter, I think you should write down what, I mean, if you write down what this is LK of F is the sum tau mk g n for some fixed function n, and sum over m goes over some finite set. Let's see, F. So now you plug this in, you will get the vector pi of certain functions, and then you will get these coefficients. But actually here, this thing won't even depend on for all V's, you will get a function, you will get things which transform for with respect to the same finite set of n's. And of course you have to compose this formula with this. You have to, there is, oh yeah. Now you look at this. This means that these vectors, whatever V is, transform under the same finitely many k-types, and this is exactly what Peter said.
Yeah, so what I haven't said and what Dragan was saying in this step here, okay, so is if I fix V in a k-isotypic component, and this is what Parker was saying. So if I fix V in a k-isotypic component of the k-finite vectors, this finite dimensional space, then the calculation that Dragan was sketching is that pi of fv again lands in that isotypic space. Okay, and so if I have an arbitrary k-finite vector, it's a sum of these finite isotypic spaces. So its image will live in the sum of finite isotypic spaces. And so the image will be finite dimensional. So finite rank. We can discuss it. I'm running out of time. This is just this impressive amount of questions today. So that's good. But
Okay, now because you are anyway running out of time, one can give a nice philosophical explanation for Rishi's question, because if you use it.
But wait, can I just define the character? let me define the character. Let me define the character. I didn't say shut up. I said I'll define the character. So.
Feel free to say shut up.
So. Okay. So let me finish with the definition of the character, and then we'll also, and then Dragan will finish with some philosophy. Okay. So this is a well-defined map. So we have, so we get a map which I'll call theta pi d. So remember our representation, we started out with this admissible representation. Okay, so we get a map theta pi d, which takes f in these k finite things to, well, because the image is in f end by this lemma that I didn't do a very good job explaining, then we can take the trace of pi of f using this linear algebra. We know what trace means. Now, but this is dense. Okay? So this extends. Well, you have to check that it extends. Well, it extends some way, but in fact, it extends to a continuous map. So we're using the density here, theta pi d, which takes a compactly supported function on G to its, to C. Okay. So on these k finite compactly supported functions, we have this notion of trace of a finite rank linear operator, which is what we're using. Using the density, we can extend that to a map from here to here. And then you have to check separately that's continuous. That's another step. Okay? And so a continuous map in the space of so-called test functions, smooth functions with compact support, that's what's called the distribution. So this is the distribution character.
How do we know the traces don't blow up as we approach the function? The functions get close, but how do we know the traces get close?
So why the trace extends?
Right, I mean, yeah, why does it,
I
how do we
mean,
know the trace
you
doesn't blow up?
need to estimate. I mean, this is not. But the main point is that Fourier coefficients
Of smooth functions, yeah.
decay very fast.
Yeah, so what I didn't explain is, we only said in words, is how this is dense in here. And the density is by taking these bi-circle, yeah, the circle left, circle right, double Fourier series, okay? And those coefficients, because you're starting with a smooth function, die very quickly. And so then you can sum them, which is the point. But you see how to extend from here to here, you have to sum these Fourier coefficients. And if they die rapidly, I mean, to get the extension of this map to here, I mean, the number that I get is basically the sum of these Fourier coefficients.
I guess what I'm arguing, the
Okay.
thing I'm not seeing is, say I'm using Fourier series to get close over here.
Yeah.
So basically, as I do that, I'm thinking, okay, maybe I'm using more and more coefficients.
Yeah.
So maybe it's making the dimensions of these endomorphisms
Don't worry.
bigger and bigger, and maybe my trace is getting bigger and bigger and bigger, and I don't know that it actually converges.
But that's the point. The Fourier coefficients are dying so fast that the sum,
Trace information is very small.
and so you get a finite. So you can sum the Fourier coefficients.
The additional trace information becomes small.
The additional trace information comes what? You said a question. Distribution. So we'll see that this is given by integration over a function. We won't actually see it. I'll assert it.
Think about logically, the reason I gave my talk before his was just so the word distribution would not seem like an alien language.
Right. So maybe it seems, based on facial expressions, that it's still an alien language.
So we've done the best we could in 2 hours.
Right.
So are you claiming that the extended map is also the trace map for CC?
Right. I mean, if you can make sense of a trace of, you can make.
No, is it in fact the trace? I mean, is it a trace class operator, and is it in fact the trace?
On Hilbert space, yes.
Yes.
But I mean, in general, it's a difficult issue if you have some stupid balance space.
But I mean, another way. I mean, I said there are two routes. You know, you make sense of what it means to be a trace, and in a Hilbert space, that it's invariant. You know, you sum the diagonals. It doesn't depend on the choice of basis. And then, if you make sense of all that, then this is indeed the trace of pi of f for f in here. But we did approach it differently.
The V in the left diagram, is that all of H or strictly the K class?
Now this is a linear algebra diagram. This is a linear algebra diagram.
But in our case, we're taking V to the H.
Yes, v to be hk.
Just the K
Yes. Because that's where pi of f is living in a finite rank endomorphism of the k finite vector. Okay, so that actually took much longer. I thought that was going to take a half an hour, and then I was going to have 20 minutes to do other stuff. So I guess I'll have to go again this afternoon to Dragon's Delight, probably.
Peter, I mean, I promised to shut up, but I think...
No, come up and, no, explain,
No,
explain.
You should certainly, you forgot to mention the last thing, that this character is actually the sum of all diagonal matrix coefficients, that this limiting process just gives you the sum in sense of distributions.
Yeah, I mean, yeah, that's right. So exactly as Dragon says, the sum of the diagonal matrix coefficients will converge as a distribution to this. That's the point.
I mean, you can write out F as a matrix. It is on the k, different k types, it's just a giant.
Pi of f is a big block diagonal matrix where the blocks correspond to the k types, and
The sum is defined because they rapidly decrease.
That's what we were getting at by this density, and this is what we get. So next time I'll start by stating that this character has the properties we want. In the finite groups case, what was the point? That they were linearly independent for irreducible representations, that they're additive on exact sequence, that they're invariant. The invariance is clear from properties of the trace, which I haven't made explicit. Dragon wants to end with some philosophy.
You know, I mean, I just, okay. I just wanted to say, because this answers Richie's question and makes this argument more transparent. If you have k binaries, then because...
Wait, I know this is a ridiculous request. I laugh at it every time, but you have to wear a microphone.
I mean, this is just a remark. So if you use the, let's see, this is right, k action, then this f is right k finite. If you do the calculation, this is an exercise Peter assumed that you all will do yourself. Then you see that this guy actually acts only on k types related to the right regular action on f. So on everything else, this operator will be 0. So therefore, the choice of this v is just in finite dimensional space. So there was no issue over there. So this is, and another thing is that you want the symmetry with respect to adjoint representation. If you go from action on v, calculating character on v and v twiddle, you will just go from one finiteness of k action to the one on the other side. So you really want to have the complete symmetry, to have this k left and right invariance. Okay, so this is everything. Say, which is important, that this character is just the sum of all of these matrix coefficients for various n's. So if I take v twiddle n pi of x v n, sum over all n's in z. So these are matrix coefficients. So they depend only on Harishchandra module. So this distribution also depends only on Harishchandra module. And this is clear from the construction, but this is really important that the form of actually module A, H is not important, just the action on HK.